Welcome. In today's video, we're going to look at maximum likelihood estimation for the p parameter in the Bernoulli distribution. So here we're going to begin with a series of independent and identically distributed random variables, x1, x2, all the way up to xn, and we write distributed IID, and we're going to say these have a Bernoulli distribution with parameter p. So if this is the case, then the probability mass function of each xi, of all the xi's, is given by, well, we know it to be the probability xi, the PMF, is equal to p to the xi, 1 minus p, 1 minus xi, where xi is either 0, 1. In other words, when xi is 0, then you have the probability xi equals 0 is 1 minus p, and the probability xi equals 1 is equal to p. So using this PMF, the likelihood function is given by, well, again, the likelihood function, and we'll call it L of the parameter p, is equal to the product I equals 1 to n of all the respective marginals. So in this case, or in other words, it's the joint, you can think of it as the joint PMF of x1, x2, all the way to xn. So we're going to substitute our formula up here. So that becomes I equals 1 to n of p to the xi, 1 minus p to the 1 minus xi. Then what we're going to do here is we're going to split this up a little bit. So I'm going to say that is the product of pxi times the product I equals 1 to n of the second half. Now, this just allows us to look at this a little bit easier, I suppose, now. So we're going to take, here we've got the product of powers, so p to a different set of powers. So using our power laws, or our laws involving indices, we know that that actually becomes p to the sum of I equals 1 to n xi, and equally, or in the same fashion, that this half becomes the sum I equals 1 of 1 minus xi here on this side. Now I'm going to do one more line of simplification, and I'm going to write, again, this is still I equals 1 to n of xi. However, this becomes 1 minus p. Now notice here that we're summing from I equals 1 to n. We're summing 1 n times. So because we're summing it n times, then we're left with n of them, and we've still got the minus xi's on this part, so we've got the minus the sum of I equals 1 to n xi. And that leaves us with the derivation of the likelihood function. So now it's going to be to come up with the log likelihoods function. So the log likelihood function is given by, okay, so remember, by definition, what I'm going to say is L of p is equal to log of the likelihood function. Remember, log here has base e by default. So now I'm going to plug in our expression that we got above. So what was that expression? It was this expression above. P I equals 1 to n xi, 1 minus p n minus I equals 1 to n xi here nicely. Okay, so now we're going to try and do some simplification here. Now, the first thing we're going to notice is we're going to use our log laws. So remember, when we have log of a product, it becomes the sum of logs. So the first thing that this becomes, this is log p to the I equals 1 n xi plus log 1 minus p to the n minus sum of I equals 1 to n of xi's here. Now we're going to use some further log laws. So because we've got p to the power, remember those powers can come down the front. Or actually what I'm going to write that now is as log p sum I equals 1 to n of xi. So I've just put that at the back instead of the front. And then, or in fact what I might do is put that in brackets just to be clear. It's log p times all of that. And the same thing can be said here. Here is the power. We're going to bring that down the front. So, or plus log 1 minus p. We still have our log minus p. But then we've got our n minus summation I equals 1 to n of xi here. Okay, well, we've found our likelihood function, our log likelihood function. What's left now is we're going to differentiate this with respect to p, then solve it equaling 0. And then we're going to find the second derivative and show that it is a maximum, or this value of p attains a maximum. So the first thing I'm going to do is I'm going to find the first and second derivative, and that can be done here. So differentiating with respect to p gives. Alright, so what do we get here? So let me just make sure I've got the expression. So we've got dl of p over dp. So let's differentiate here. Okay, so we're going to look at that first term. So the first term, you've got log p. How do you differentiate a log? That just becomes 1 over p I equals 1 to n xi. Pretty straightforward. Then the second part here, what we have is log 1 minus p. Now log 1 minus p is a little bit different. So you've got, of course, you have to take 1 over what's inside the log, but then you've also got to take a look at the inner differential, and you see 1 minus p. So the derivative of the inner function is -1, and that's why this becomes a -1 at the front. And now that leaves us again with n minor, and that just can be treated as a constant. Remember, the sum of xi's and the n minus sum of xi's can be treated as constants because they're not functions of p. Now we're going to differentiate again. So the second derivative of the log likelihood function looks something like this. So again, we've got to differentiate 1 on p. The differential, or 1 on p differentiated with respect to p, becomes 1 on p squared. I equals 1 to n xi. Now this one's a little bit trickier. This is the differential, or we've got to differentiate -1 over 1 minus p, and when we differentiate that, we actually end up with 1 over 1 minus p squared, still with a negative out the front. The reason being is that first we notice that this is 1 minus p, -1 minus p to the -1. So we'd have to take the power down, or we take the power down to get rid of it, and then that would become a -2, but then we've still got to multiply by the derivative of the inner function, which is -1. So this negative cancels with this negative, but then we've got a third negative to take into account here, and that's why there's still a negative at the front. And then, of course, the remainder or the remaining part of this function just looks like it was the constant it was previously. So, we've found the first and second derivative. Now we've got to find the MLE, or the maximum likelihood estimate, and to find the MLE of P, which is given the symbol, we'll give it P hat. We solve the fact that the dl of P over dP at the maximum likelihood estimate is equal to 0. If and only if, okay, let's take our function that we have up here. We're just going to take that function, that nice function up here, copy that, paste it there, and of course, but we're evaluating that function at p hat, and that has to be equal to 0. So the first thing we're going to do is we're going to do a bit of rearranging. So the first step here is to take this particular expression to the right hand side of the formula. So that gives us n minus I equals 1 to n xi. Positive on that side is equal to 1 on p hat sum of I equals 1 to n xi. Okay, so this will involve a little bit of algebra here, I suspect. So the next thing I'm going to do to solve for p, I'm going to actually take this 1 minus p and multiply it by this side, and I'm going to take this x sum of x and divide it onto that side. So the next line in our solution looks something like I equals 1 to n xi sum over the sum of I equals 1 to n xi is equal to, again, so moving this 1 minus p to here, 1 minus p hat over p hat. Okay, this is slightly starting to look promising. Now, the reason I did that, of course, is because I want all the p hats on one side when I'm doing these sorts of solutions. So the next thing I'm going to do here is I'm going to do a little bit of simplification, some clever simplification. And I'm going to begin with, I'm going to notice that I can write this as n over the sum of I equals 1 to n xi minus 1. You see here, this divided by this just becomes minus 1. And equally, on this side of the equation, I can write this as 1 on p hat minus 1. So you've noticed here that's 1 on p hat up here, but p hat on p hat just becomes 1. And now actually we're basically at our last step here, and we can recognize that p hat actually has to be 1 on p hat is n on the sum of xi's, so p hat is 1 on n times the sum of the xi's, and again, this by definition is the sample mean. Now we're almost done here. The last thing we have to do is prove that this is in fact the maximum. So to do that, to prove that L of P, or the likelihood or the log likelihood function, either one, is maximized at P, which is P hat, which is X bar, the sample mean, we must show, remember, we have to show that the second derivative of the log likelihood function with respect to P, and I should say evaluated at P is equal to P hat, is less than 0. But note, let's take a look at the second derivative. Here was the second derivative up here. So I'm going to take this particular function, I'm going to copy it, and I'm going to paste it here. And we're going to take a look at it a little bit closer. So the first thing I'm going to do is I'm going to see I've got a negative here and a negative here. I'm going to take that negative out the front, or I'm going to factor it out. So I'm going to say that's negative plus, so negative all of that. Now, this is where it becomes interesting. So my claim, I'm going to claim in general that this is less than 0 for all values of P. No matter what the value of P is, I'm going to say that it's negative. Now, how can I say that? Well, I'm going to have a look at everything. This particular expression here, 1 over P squared greater than 0. This particular expression here is the sum of Bernoulli trials greater than 0. This expression here, greater than 0, because 1p is between 0 and 1, 1 minus p is between 0 and 1, 1 minus p, and therefore, well, it's a squared anyway, so even if it was negative, we know it's greater than 0. And this expression here, well, we know that the sum of Bernoulli trials, in this case, is less than n. So what do I mean? Because, remember, xi can only take values between 0 and 1, then at the absolute maximum, the maximum value that this could potentially be is the sum of 1s, so they're all 1, all xi's are 1, and so the absolute minimum the whole thing could be is n minus n, which is 0. So for argument's sake, I'm going to say that at least one of them wasn't 0, and so I can claim that this is greater, or I can even say that that's greater than or equal to 0, and really I should say that that's greater than or equal to 0 here, because technically I could get a bunch of zeros. So together, that means all of this whole thing here is greater than 0, but we're taking a negative, so it's less than 0. And so because that's true for all p, no matter the value of p, then when we evaluate it at the maximum likelihood estimate, it's also going to be less than or equal to 0, irrespective of the actual value itself. And so the MLE of P is P hat, and which we will say xn bar. And again, I'm going to use the capital version, capital X, to denote that it's a random variable. And that concludes finding the maximum likelihood estimate for the parameter of the Bernoulli distribution.